Good afternoon, everybody, and welcome to the what is the final session in our week of webinars, Achieving Net Zero, in conjunction with the IQ and IAT. A much different topic, but equally important and relevant, and perhaps can be regarded as very cutting edge, I think, in terms of the subject matter. So I'll hand over to Dr. Craig Dawson. Craig is currently working alongside Nobel Prize winning team in the University of Manchester's new Graphene Engineering Innovation Centre. And as part of his work, he's been working alongside national highways over the last 3 years on the development of graphene, modified bitumen and asphalt. So I'll hand over to you, Craig, and be really interested to hear what you have to say.
Really, I just kind of want to stimulate everyone's thinking around how novel materials, advanced materials, nanomaterials, and specifically today, graphene and two-dimensional materials might help address kind of net zero and sustainability targets. So I'll start by just talking a little bit about the history of graphene, what graphene is, and then I'll go into how we have used it, how we might use it in specifically in asphalt and bitumen, and then talk around some of the case studies and the commercial concerns that people might have, and where graphene is with regards to exploitation in the wider world. So graphene was, it was kind of postulated and known to exist. So graphene is a monolayer of graphite. So, graphite's a well-known, well-used material. And the properties of graphene were kind of theoretically known, but it was thought to be impossible to isolate because of its stability in the atmosphere. And in 2004, two University of Manchester academics isolated the material and measured the properties. And, that led to, in 2010, the award of the Nobel Prize for Physics, a lot of inward investment into Manchester, which has resulted in the building of two centres for graphene, the first being completed and opened in 2015, the National Graphene Institute, which kind of deals with more of the fundamental science and the academic side of things. That's a £61 million investment, and it includes things like a nice clean room, something that, us material scientists and I'm guessing quarrying and asphalt experts don't really see very often, but this is kind of to really pin down those fundamental properties of graphene. And it's really the leading centre of its kind in the world. The University of Manchester has over 330 academics working on graphene 2D materials and how they might be applied across, a whole host of areas. And this is basically what I've said. This is a little out of date, so we've got much more than this in terms of publications and patents right now. and there's significant commercial interest. We're working with lots and lots of different companies, both kind of small scale semiconductor industry, across multiple sectors. So this led to the building of a second institute, which is where I work, the Graphene Engineering Innovation Centre. And this is really to help companies bridge the technology gap between academic research and the commercial exploitation of that research into real world products and technologies. So the Graphene Engineering Innovation Centre, so if we think of how a technology is developed, there's kind of this lag between universities and industry, which requires, especially with regards to disruptive technologies, significant investment, which is risky. And a lot of the time that gap isn't bridged because that investment in the research is deemed to be too high. And guess whether you guessed or not, the geek fits into that gap perfectly and helps companies and other entities bridge that gap. And I'm not going to say it's seamless, but help bring technologies to the market. This is slightly out of place, but yes. So it was these two academics were the people who isolated and found all these amazing properties. So graphene, as I've mentioned before, is a single atomic layer of graphite. And it's got all these kind of really nice properties. It's, the strongest material known to man. This is something we don't really like to say, but people compare it to stronger than steel. At a monoatomic level, it is stronger than steel. At a bulk level, steel's pretty good at what it does, but it's very, very conductive, both electrically and thermally. So we can do some nice things with you exploiting those properties. It's very, very strong, but at a bulk scale, quite difficult to realize all those beautiful properties within a composite system. So how do we produce graphene? So graphite is this multiple layer. So it's got made up of lots of millions of single layers of graphene, and we are after just one slice of that. So we can either produce that from kind of carbon source like a methane, grow that onto a substrate like copper. But as you can imagine, that's quite close to getting those ideal properties. But as a bulk material for dispersion in another system is completely, it's not commercially viable. That we cost that as a meter squared, not as per kilo. But we can also produce it from that bulk graphite. So I guess the famous story is that the 2 Nobel Prize winners used sticky tape to exfoliate individual layers of graphite down to this single layer, and then they measured the properties of that individual layer, and that's what they won the Nobel Prize for. Since that time, that's if we're all here doing the sticky tape, we'd spend a lot of time to produce, grams of material, let alone kilos and hundreds of kilos and tons of material required for most applications. So in the meantime, since kind of 2004, there's been a lot of work in developing processes for producing these, what we call graphene nanoplatelets, which again, they move away from this ideal monolayer towards a more multi-layer system. They do lose some of those properties, and as we move towards bulk graphite again. But as long as we're down below a certain number of layers, we do retain a lot of those properties, and we can transfer those to the system that they're going into. So how do we see graphene helping move towards net zero? So it's a question we've been increasingly asked. We're probably out of the hype circle for graphene, and definitely sustainability is our main agenda at the moment. And how graphene can affect the material properties of an application, at a nano scale, how that affects it at the macro scale and beyond. So by adding small amounts of graphene to some systems, we can drastically reduce the amount of material that's required for a specific task. Alongside that, graphene's got unbelievable things like barrier properties, so nothing can go through graphene. Molecularly, even helium can't go through. So, we can impose those properties onto a system as well. So we can enhance the durability and because we're only adding small amounts, and it allows certain amounts of re-engineering to be done. So we can take material out, we can change systems up if we're being really disruptive. And in some cases, we can reduce the whole lifetime cost of an application, as well as enhancing the sustainability of that application. So graphene can also be made in another way. We can make it chemically, and we produce this oxidized version. So back to chemistry 101, graphene is this perfect honeycomb lattice. So ignore all those O's, OHs and COOHs, and just imagine that as a perfect lattice. And that is what pristine graphene is this sp2 carbon structure. When we produce it chemically, you use quite aggressive chemicals, and it introduces these oxygen-containing groups, and that's called graphene oxide. I've mentioned that because I'll mention that through the rest of my talk. And graphene is an aqueous. It's hydrophobic, so you can't put it within aqueous systems. Graphene oxide becomes hydrophilic, so we can use it in aqueous systems. So where that's appropriate, we can use this material. We can also functionalize this material quite easily, so we can change some of these chemical groups into other chemical groups, or systems can interact more readily with those chemical elements of the graphene oxide, which graphene as a pristine material is very chemically inert, and that's not quite as easy to do. So I thought I'd address the elephant in the room as well. We always get asked this question: how much does graphene cost? So at the moment, we can source graphene at the kind of kilo-ton scale. Price is down to £50, $50 a kilo. So that's enabling quite a lot of applications. This graph here is, I'm sorry about the qualities. It's the only one I could find in the time. This from the graphene flagship shows that maybe things like cement, concretes, bitumens and asphalts are potentially still too high at that, but we're really seeing a move and economies of scale starting to kick in. And some of our suppliers and the supply chain are talking kind of $16, $20 a kilo. So that's really going to open up all those markets quite soon, I think. And we've seen with one of our current projects where we were putting graphene within cement and concrete, that the use of graphene and the effect that graphene's had on the system has meant that they can do extra things. So especially with the sustainability in mind, we've cast concrete floor slabs, which is with enough early tensile strength that's allowed us to take the steel support out of the floor slab. So there's a cost saving from a labour and materials point of view, as well as a sustainability saving, CO2 saving, because we can remove that steel and we can remove up to a third of the concrete as well. So it's quite a good success story. So why use graphene in bitumens and asphalt? So I'm hoping some people will be able to recognize these graphs. So these are DSR curves. So we see that graphene, by adding these are really small amounts, so up to 1% graphene in this instance. So these are all from the academic literature. It's all in the public domain. That we are getting improvements across the entire temperature range. We also see this across the entire frequency range. We see improved aging, so thermal aging. We see improvements there. We see improvement in UV stability. So I'll explain these a little. These are infrared analysis and looking at specific peaks around carbonyl and sulfoxide growth. So we see that the growth of these peaks is seen when we get UV degradation. That is subdued by the use of graphene within that bituminous system. Antirooting effects. We see improved interface between these are academic claims. Improved interface between the aggregate and the bitumen, and in some cases they're even claiming anti-skid properties. But I'm not entirely convinced of that at this stage. Not that we've tested it. I think it's a dispersion issue and a texturizing issue that they claim is there, and I'm not sure it would be there if you use the graphene more effectively. So we can add graphene directly into a bitumen and then disperse that within an asphalt. But a lot of work's also been done in introducing graphene into a carrier system and then dispersing that into the bitumen and the asphalt. So I'm going to concentrate probably more on these rubber ones as one of my case studies later on. Graphene within a rubber and then disperse that within an asphalt. And we can see with these graphs again these improvements in DSR results and in tensile strength. And we've also dispersed graphene within these cementified emulsified asphalts. And I'll go directly to these case studies now. So the first one I wanted to talk about, this is not something that the University of Manchester was involved with, is the case study down in Oxfordshire, where Director Plus, between Director Plus, which is an Italian graphene company, Interchimica, who are an Italian chemical company, and Skanska, they laid 750 metres of road down in Oxfordshire. We believe that Director Plus put their graphene that they produce within an SBS rubber and then dispersed that into the asphalt. And they saw significant improvements in flexural strength, which they think will help the durability of the road and prevent the failure of the road. This is a project that we were involved with National Highways on the A1 just south of Alnwick. where we put graphene within a cold in situ recycled process, dug up the road, developed a method for putting the graphene within that process that wasn't disruptive at the point of use, and laid 250 metres of road. So this is currently about a kilometre of graphene modified road in the UK. And these are kind of living labs, and we'll be testing those road surfaces to see how they compare to, we've laid lanes side by side. We'll be able to do direct comparisons between graphene and non-enhanced materials side by side. I mean, we did a lot of laboratory pre-work, and we were seeing in the laboratory around stiffness increases of about 25%, which gave National Highways enough confidence to put this material on a live project. And we've got cores that are currently undergoing testing to see the effect that we're having in the field, using a real kind of the variability of a real road produced using the in situ recycled process. And, early indications are that we're kind of matching laboratory performance in the field. So I'm going to move again away from the science and the asphalt applications, and you kind of, we are really seeing the impact of graphene in real world applications. We use this term, we're at the tipping point, and has it taken a long time? We're only 17 years into the journey, really, from discovery. And if we take materials like carbon fibers, carbon nanotubes, and other advanced material types, we hope we've learned some lessons, and we can accelerate the application of these materials, which is specifically kind of what the geek is set up to do. So some of the other applications wider than this is, Ford are now using graphene enhanced materials on all of their cars produced in the US. They put it within a fairly simple component, which has allowed their engine block to be reduced in size, which, as a secondary benefit, the cars seem quieter in the cabin, and you get better driver comfort. Huawei are the world's biggest user of graphene, and they use it for its amazing thermal properties, and they have a heat spreader in their top end phones, which moves heat around more effectively, which allows the processor to be run quickly, and basically the phones are faster and more powerful as a result. This is a University of Manchester collaborative project where we worked on with a company called Innovate Trainers, and they've put it in their rubber. So usually you trade off wear against grip, and by adding a small amount of graphene, they've been able to improve the wear without trading off the grip. So they've got a grippy trainer that lasts twice as long. And the question is, why would they want their trainers to last twice as long? So it's more sustainable, but also they managed to sell twice as many trainers. So they weren't because of the addition of the graphene. So yeah, we're really seeing this step up where people are less dubious on how graphene might help them, and really asking the question of how can graphene help our products and help us move forward with the technology. We offer a membership model where people can join the Graphene Engineering Innovation Centre. We're 100% commercially focused with no academic engagement. If you want academic engagement, we can put you in touch with an academic, and you can go, be placed in the National Graphene Institute or within one of the schools. But with our partners, we've been operational, with COVID for just over 2.5 years, and we've secured for our commercial partners over £2.7 million of Innovate UK funding. It's just basically repeating some of that. We also have a program Bridging the Gap, where it is for Greater Manchester. Companies can come and work with us for free and access the facility here and the personnel that we've got and the expertise within the University of Manchester. And, the aim is that we're going to build this graphene city. The university has really high sustainability targets. We've just opened a Manchester Sustainability Hub as well. So it's really an important thing. And we see graphene being an important part of that story. Thank you.
Thanks very much, Craig. A really interesting presentation there. And I think, particularly from my perspective, we've been having these conversations all week around sustainability. And one of the conversations that's come out is that the enthusiasm for sustainability and innovation is really strong in many cases, but there's the application side when you're actually asked to put your money where your mouth is from a real world application. Perhaps it's a little bit more reticent. So I think from a perspective of what you're talking about, that link between pure academic and research into the real world application is fantastic, because it starts to showcase how this does really work and hopefully induce confidence in people in adopting these new technologies as soon as we physically can. Because again, I think, as we started the week, the clock is ticking around sustainability and some of the agendas we're looking at, and we need to just simply move on some of these things. I have a question from John Bullis. I realise that it isn't proper, in inverted commas, graphene, but can you partially realise any of the benefit of graphene by using partially exfoliated graphite or boron nitride instead? From a lower material cost point?
Yeah, so I'll address the graphite versus graphene thing. So there's, especially within lower tensile strength applications, you can definitely, graphene, when it gets really thin, becomes quite flexible. And where you want stiffness, that flexibility can actually impact how much stiffness you get in. And it's called shear lag theory, if you want the proper term for it. That shear lag means that when you need to build up the layers, and there's probably a sweet spot where that the thickness of a graphene graphite and the stiffness related to that thickness becomes important. So, where graphene isn't a solution, that's one of the things we're set up to kind of discover. And a lot of these graphenes have a lot of graphitic properties to these nanoplatelets, which is why we differentiate them from graphene. As a purist, they will have a lot of graphitic character in there. There will be graphene in there. There will be nanographite in there. From an applications point of view, it doesn't matter what you're using as long as you get the result that you want. That's kind of one of our ethos. And whether that's graphite, graphene, or another material, that's something we're here to help try and find out. We adopt this kind of fail fast, test and fail, and do it fast, and then iterate ethos. So we kind of, rather than taking 3 years that a PhD might do to get to an answer, we can do these short stop experiments and find that out whether something's feasible or not quite quickly. Regarding boron nitride, yes, other 2D materials are available. So boron nitride is a really interesting one. It's got a lot of the similar properties to graphene, so it's still quite a strong material, but it's electrically isolating rather than electrically conductive. So we can start doing some quite neat and clever things where we can stop electricity moving around, but we can still move heat around very effectively. So boron nitride isn't a cheap material either. Especially in a nanoform. But there are other materials that are of interest. So all layered materials, there isn't any real block on them being made into two-dimensional form. So things like nanoclays, and clays are a very abundant material. They're starting to see some real traction in use in membranes and in areas where clays might have been used previously. But things like two-dimensional perovskites for solar cells. So there's a whole family, I think it's about 2,500 two-dimensional materials, which are, again, just moving out of an academic phase. And maybe some of them will move here into the Graphene Engineering Innovation Centre, and we'll start seeing exploitation of those as well. I hope I answered your question there. and apologies, I didn't mention PTS. They were on the slide deck there in the collaborative partners, but yeah.
It's come up in the chat, and that's great. And I think it's good that we've got to be able to ask the question, and I think it shows the depth of the technology around this side of things and how deeply technical it is, and also that this is it's at the cutting edge of things that are going on, isn't it? So there are new and different opportunities that come up through these processes. So I think that's absolutely fantastic. So from Colin Redmond for you, Greg, during the cold in situ recycling trial, how was the graphene introduced into the mix? Was it via cement?
That's commercially sensitive.
There we go.
Yeah. So I will talk a little bit more about the partnership we have with Huawei. That it's quite an altruistic approach that Huawei have taken in parallel with PTS, in that they're developing technology that, basically for the users of the road, not for commercial exploitation themselves. So they're a little bit at the whim of the supply chain at the moment, and they've specified a product and the product's performance, and they've kind of got to lump it, and they're looking for, a different way of thinking where they can kind of specify a performance that they want rather than being specified a performance that they can have, and that can then have a knock-on effect on the durability of the roads and the effect on the public purse.
And I'm saying, again, there is always going to be some sensitivities around some of these things. Perhaps a slightly more open question. One of the factors that we talk about in the sector a lot is health and safety as a priority. And John has asked us, are there any potential health exposure risks documented in and around sort of the use of graphene in these environments as yet?
Yeah, I mean, graphene's a nano material, so there's always, there's always going to be concerns around breathing any nanomaterial in, or any dust particulate material is potentially dangerous. So handling the powder is always going to be an issue. From an occupational health side of things, once we put it into a system, it's pretty much encapsulated within that system. So the hazards are reduced. When we're using it with things like cement, cement's a fairly nasty material in its own right, and the occupational handling of that material, we don't really see it being needing any extra help, PPE at the moment. Care has to be taken anyway. There's nobody really saying graphene is safe, but when you use a pencil, that's graphite. There's probably, when you've written something, you've produced some graphene at some point in your life. So it is a naturally occurring material. With regards things like asbestos and carbon nanotubes, it doesn't have the same aspect ratio as those materials, so it's less likely to cause some of the issues seen with those, on contact with lungs and things like that. But there's still a lot of work to be done with regards to the actual health implications. But I mean, it's been used in drug trials for drug delivery, smart drug delivery, here at the University of Manchester. And we are careful, but we're not pessimistic as to the effects on the health and safety. We're leading the world on a lot of these studies.
From Gary McNeely, do you know why the Oxfordshire trial did not use recycled materials used in the in situ recycle trial?
Yes, I would say that's probably commercially sensitive.
Yeah, I wonder what it might be.
Yeah, it's not for me to comment on another technology.
Absolutely, no, that's fine. We'll scratch. So, and then finally, we'll close out with this one. Have you carried out any accelerated long-term testing of the graphene-based materials, cementitious and bituminous, to understand their durability, performance, and service life?
Yeah, I'll stick to the bituminous materials. So that those tests are ongoing. So we're subjecting those to ASTM standard tests, cycling, durability, UV stability tests, and those results, it's ongoing. They're advanced degradation tests, but they still take a long time to complete.
Okay, excellent. That's brilliant. Thank you ever so much.